In this video, we will learn how we can make organometallic reagents. So organometallic reagents means we have the organomagnesium reagents, that is our Grignard reagent, and we also have the organolithium reagents. So there are four methods. The first method is the oxidative insertion approach to synthesize the organolithium and organomagnesium compounds. The second method is from alkynes. The deprotonation of alkanes can give us the organolithium compounds. And we can have the third method, that is the halogen metal exchange method for the synthesis of organolithiums. And the last method is the transmetallation approach. So these four methods can be used to synthesize organometallic reagents. So we will discuss each of these methods in detail. So the first method is the oxidative insertion. So I have taken an alkyl halide. X can be fluorine, bromine, or iodine, and you treat this with magnesium metal. You will generate the Grignard reagent. So this is the Grignard reagent. In this reaction, the magnesium is in zero oxidation state. So after the reaction, the magnesium becomes +2 oxidation state. That means the oxidation number increases. That's why we call this process oxidative insertion, or we can call oxidative addition. So in this reaction, the magnesium adds to the carbon halogen bond, and you are generating the Grignard reagent. The important thing you need to remember, in the Grignard synthesis, we use either based solvents. For example, you can use diethyl ether. So this is the diethyl ether. So the structure is like this. So you have ethyl group at both the ends. So this is the diethyl ether. And you can have the cyclic ether, that is the THF. We call it as tetrahydrofuran. So this is the cyclic ether containing a 5-membered ring. And you can have dioxin as the solvent. So this is like you can draw 2 oxygen here and connect this way. So this is dioxin. It is also known as 1,4-dioxin because the oxygen is attached at the first and the fourth position. And the other solvent you can use is the DME. This is the dimethoxyethane. So you have an ethane. So first draw the ethane 1 and 2. And you have dimethoxy. So attach one methoxy group here, another methoxy group here. The reason why we need ether as the solvent, this is because in the Grignard reagent, the magnesium is in +2 oxidation state, and this is more stable than the +0 oxidation state. But magnesium prefers a tetrahedral geometry. So if we use ether as the solvent, so you can name this like, consider this group as R and this group as again one more R. So this is like OR2. So this magnesium will coordinate with two solvent molecules like this, and it can make a tetrahedral geometry. That's why when we prepare the Grignard reagent, we use ether based solvents. Next, we will learn the oxidative insertion approach for the synthesis of organolithium reagents. So I am taking here an alkyl halide. Okay, so we can have X is equal to fluorine or bromine, and we can use our lithium metal. So lithium metal is in plus zero oxidation state, and you will generate the organolithium. So you have to see in the starting material you have the halide. So you need to use two equivalent of lithium. So you will generate one equivalent of lithium halide as the side product. If you see the oxidation state, here the lithium is in plus zero oxidation state. Now the lithium become plus one oxidation state. That means the oxidation number increases. That's why this process is called oxidative insertion, or we can also call oxidative addition. And regarding the solvent, we can use the ether-based solvents like our Grignard reagent, but we can also use hydrocarbon solvents like the hexanes, or you can even use the pentane. This is because if you see the magnesium based Grignard reagent, the magnesium is in plus 2 oxidation state, and we mentioned that it needs the ether solvent for having a tetrahedral geometry. However, in the case of organolithiums, the lithium one, it doesn't need an extra coordination for stabilization. So that's why we can use hydrocarbon solvents such as hexane and pentane for organolithium synthesis. I will introduce you to some commercially available organometallics. Commercially available in the sense you can directly buy from industries or some pharma companies like Sigma Aldrich, the Tokyo Chemical Industry, Fluorochem or BLD, or many other industries are there. So for example, if you consider the organolithium reagents, you can have the methyl lithium, you will get in diethyl ether solvent or in dimethoxyethane solvent, and you can have the n-butyl lithium. So n-butyl lithium means like you have a butyl group 1, 2, 3, 4, and which contain a lithium. So this you can get in cyclohexane or even in hexane. Then you can have the secondary butyl lithium. So this you will get in pentane or cyclohexane. And you can have the tertiary butyl lithium. You can have it in pentane. And the phenyl lithium, you can have it in n-butyl ether. Okay. So if you see in the organolithium case, you can have even the hydrocarbon solvents or the diethyl ether solvents like the ether-based solvents or hydrocarbon solvents. And let's see the Grignard reagents, that is the organomagnesium reagents. So the first one you can get the methyl magnesium chloride. So it will be available either in diethyl ether or tetrahydrofuran. And you can have the butyl magnesium chloride. So this one is available in diethyl ether or THF. And you can have the allyl magnesium chloride. So this will be available in diethyl ether. And you can have the phenyl magnesium chloride or the phenyl magnesium bromide. So this will be available in diethyl ether or THF. So if you see the Grignard reagent, all the solvents are ether solvents. So this you need to understand. So another important thing you need to know about the organometallic reagents is their ability to act as base. So they can act as base. That means they can take the proton. So if I open a bottle of organolithium, that is the methyl lithium, under air, so this air contain moisture. So the moisture means it contains the water, right? So you have the water. So the lithium, which is delta positive, and methyl, which is delta negative. So this bond will take the hydrogen and you will generate the OH minus. So what you will get? You will get the methane, that is the CH4, and you generate the lithium hydroxide. So if you see this reaction, this is not a reversible reaction. This is because if you try to remove the hydrogen again by using a base, it's very hard to remove the hydrogen from the methane to generate the Me minus and the H plus. This is because the pK of methane is nearly equal to 50 and it is very difficult to take proton from this methane. So you must be very careful when using a bottle of organolithium reagents or the organomagnesium reagents. So if you have suppose the methyl lithium here, so you have to use a needle, right? So you use a syringe and you are taking the methyl lithium. So you have to use a balloon that contains either an argon or nitrogen to prevent the contact of methyl lithium under air. Otherwise, your methyl lithium will get completely destroyed and form the methane and the lithium hydroxide. So the main thing you need to understand, if you have a lithium reagent, for example, the N-butyl lithium, so they have the capacity to act as a strong base. I mean, they can deprotonate anything. They can take the hydrogen from anything. Now you have learned that the organometallic reagent can act as base. So we will now learn the second method for the synthesis of organometallic reagent from alkynes. So I will show an example here. So you can see I took an alkyne. So this is a 1 hexyne, and you know the alkyne is sp hybridized. So if you compare the sp2 and sp3 hybridized compounds, with the increase in the p character, their acidity will decrease. That means the sp hybridized compounds have higher acidity. So this hydrogen in the 1 hexane is acidic. So if we use our organolithium reagent, so this lithium has the positive and butyl has the negative. So this will take the hydrogen from the hexane and it will generate the minus here. So you will get this, which is stabilized by the La plus, right? And you will generate the butane. So this will form a covalent bond here. And you will generate the organolithium. So in this case, what is actually happened, you use an already known organolithium reagent and you treat that with an alkyne, you generate another organolithium reagent. So it is important that you need to use an organolithium reagent to prepare a new organolithium reagent. So we can see an example for the preparation of organomagnesium reagent or the Grignard reagent. For example, I take a propine. So this is the propine. So this is a gas, and I have taken the ethyl magnesium bromide. This is our Grignard reagent. And as I mentioned before, this is sp hybridized. So this hydrogen is acidic. So you have a positive character in the magnesium and you have a negative character here. So this will take this hydrogen, right? And you will generate the corresponding Grignard reagent. Plus you will generate the ethane. So this is the propynyl magnesium bromide. So by using ethyl magnesium bromide and you treat that with an alkyne, you generate another Grignard reagent, that is the propynyl magnesium bromide. Now we will do some examples to make your understanding better about this topic. So I have shown here this compound. So in this compound, you have an sp hybridized alkyne, you have an sp2 hybridized alkene, and here also you have an sp2 hybridized alkene. You know the acidity order is sp greater than sp2 greater than sp3. That means the hydrogen here is more acidic than this hydrogen and this hydrogen. So if you treat this compound with ethyl magnesium bromide in diethyl ether, so we have the ethyl magnesium bromide. So this is delta positive and this is delta negative. So this will take this hydrogen. So we will get the product with the MgBr here, and this is your new Grignard reagent. So I have shown here a female sex hormone, that is the estrone. And if you treat this with an alkynyl lithium in excess amount and you add water at the end of the reaction, so what you will generate, so you have here the delta positive and you have the delta negative here. So this will go for a nucleophilic addition reaction, right? So this will go here and this bond will break. So what you will generate, here O minus, and you will generate here the alkyne. So since this methyl group is in the wedge position, you will generate the alkyne in the dash position. Ethynyl estradiol. So you have a hydroxyl group here. So this is a main component that used in the oral contraceptive pills. So the third method for preparing the organometallic reagent is the halogen metal exchange. So if you take here a bromobenzene and if you treat this with butyl lithium, so here you have the halogen, right? So this is the bromine, this is the halogen, and you have the butyl lithium. So you have the delta positive here, delta negative here. So this bond will attack the bromine and this will go here. So you will generate an anion here, which is stabilized by the La plus, and you will generate the butyl bromide. So this will later form the bond, that is the phenyl lithium. So here actually the halogen and the metal just simply swap the places, right? So from here the bromine is changed to the lithium and the lithium is changed to the position of bromine. That is why it is known as the halogen metal exchange. So here I am taking a vinyl bromide. So this is the vinyl bromide. So if the bromide is attached directly to the double bond, we call it as vinyl bromide. And if it is attached like this, we call it as allyl bromide. So here it is directly attached to the double bond. So we can call it as a vinyl bromide, right? Or if you consider the nitrogen, you can also call it as an allyl amine, right? Allyl amine. So here we treat this with terbutyl lithium. So what will happen? This bromine and the lithium simply swap their places. So you will get the lithium here and the place of lithium you will get the bromine. So this is the halogen metal exchange. The fourth method for preparing the organometallic reagent is the transmetallation. I am taking here a bromobenzene and I am treating this with butyl lithium. So you have a halogen here and you have metal here. So it will undergo a halogen metal exchange. So these two will simply swap their places. So you will get in the place of bromine, you will get the lithium plus in the place of lithium, you will get the bromine. Treat the organolithium reagent with a salt of less electropositive metal. Salt of less electropositive metal. This means the zinc is less electropositive than magnesium and lithium. So the more electropositive lithium goes into the solution as their ionic salt by taking one of these halogens. So what will be the result? You will get a lithium bromide and you will get the corresponding organometallic reagent containing the zinc. So if we call this group as R, so you are generating RZnBr, or we can generally call it as RZnX. So which is similar to the Grignard reagent, right? So Grignard reagent, instead of the zinc, you have the magnesium, but here you have the zinc. So using an organometallic reagent, you can convert it into another organometallic reagent. This process is called transmetallation. So the thing you have to remember, if you need to do this conversion, you have to treat the organometallic reagent with a salt of less electropositive metal. So what will happen? The more electropositive magnesium or lithium goes into the solution as their ionic salt, while the less electropositive metal, that is the zinc, takes over the alkyl group.